One of the most beautiful things about mathematics is our ability to use it in order to create models that help us to predict the future or understand the past. Really, what we look for are trends in information. We're going to look today at a process known as linear regression. Linear regression is simply the process of analyzing data and then writing an equation to describe a relationship between the pieces of information that we have. Take a look at our first example here. Every 10 years, the United States government sends out a survey to all of the households in the United States. You're supposed to fill out that survey and send it back to the government. Some people do that, but some people don't, which causes someone to have to go knock on their door in order to collect the information. The scatter plot that you see on the screen starts with 1970. In 1970, almost 80% of people returned the census form. In 1980, about 70% did, about 65 in 1990, and just slightly over 60% in the year 2000. Let's see if there's a relationship here. Notice what we've done is we've constructed a line that fits through the data points. Some of the points are below, some of the points are above, but it fits the information pretty well. We say that because the line has a negative slope, that it has negative correlation, meaning the slope of the line is negative. Also, notice that the line is very close to all of the data points. There are no points that are just kind of scattered everywhere. They're all pretty close to the line that we've drawn. We say that that has strong correlation. So in this case, we would say that we have a strong negative correlation. In our second example, we have a series of data points that shows the number of calories in cereal bars and the number of grams of sugar. Once again, I draw a line that fits through those data points, and I notice that the slope is positive. So we say it has positive correlation. On the other hand, we notice that the points are not very close to the line. There's some that are quite a ways away on the bottom, quite a ways away on the top. So we say it has weak correlation. In our third example, we have the year and the number of hurricanes. Here, the data points are just kind of scattered everywhere. All right, again, we draw a line through it, and we could say maybe in recent years there's more hurricanes, maybe there's not. There's not a very strong correlation at all. Finally, the number of electronic tax returns that are being filed, as the internet has become more accessible to more and more people are filing their taxes by using the internet. And so we want to look at that. Here's the data, the number of tax returns in millions, and we fit the line right through it. And notice that it has a positive slope. So we say it has positive correlation. The points are very close to the line. So we say we have a strong correlation. We have a strong positive correlation. In order to perform a linear regression, we use our calculator, either the TI Inspire or the TI-84. All of the instructions on how to do this process are in your notes. On this screen, I'm showing some screenshots of what the calculator looks like as we work through each process. Example 5 is information from the United States Office of Management and Budget. It tells the amount of money spent on space and other technologies by the federal government, and the data is displayed in the table. In the first list, I've given the year, and so notice I've entered my data into a list, and on the TI Inspire, I've named the first column X, the second column Y. On the TI-84, the columns are automatically named for me. I input all of the information, and what I want to know is, can I use the data that I've been given to make predictions about what will happen in the future or to understand what happened in the past? Once I've entered the data, I now look at a scatter plot. I can clearly see that there is a positive correlation here, and I look at it and I see that it kind of flattens out and maybe starts to go down at the top. I can create a line of best fit on the Inspire to see how that line fits through the data. And notice that the equation is given to me right on that very screen. On this screen here, which is in the calculator, it actually gives us the same information. Notice it tells us which number goes with the x, 0.45969669697, and which number is the y-intercept, in this case, -905, and then some decimal places. We can use that to write our equation, y equals 0.459697 minus 905, 0.146212. Typically, they'll tell you how many decimal places to round your equation to. Now, the next thing I want to tell you about is this. We want to know the correlation. How well does the data fit the equation? We look for what we call the correlation coefficient. The correlation coefficient is R. R is the correlation coefficient, in this case 0.95. What does that mean exactly, however? Well, first of all, notice it's a positive number. Because it's a positive number, we say it has positive correlation. Correlation coefficients range from -1 to 1. This is just like the number line. If we're between 0.8 or 1.0, it's a very strong correlation. If your correlation is 1, well, then your line went through every data point. There was nothing off the line. If your correlation coefficient is 0, it means that there's no points at all. They're just kind of everywhere. They don't make any sense whatsoever. It's like having random points all over the place. Anything negative is negative correlation. Anything positive is positive correlation. It's a good idea to know this table and to have an idea what represents weak correlation, moderate correlation, and strong correlation. In our case, our R value was 0.95. 0.95 is on the right in the strong box. Therefore, it looks like I have positive, strong correlation. So my correlation coefficient has been recorded on the example, and I've explained that the correlation coefficient is a very strong, positive correlation. It fits the data well. Now we want to predict the amount of spending in certain years. We use our equation, 0.459697x minus 905, 0.146212. We plug in the year 2000, and it comes up 14.2. My prediction, based on the data, is that we'll have $14.2 billion in this area. In the year 2050, if the trend continues, what will our spending be? Notice this time I plugged in 2050 in for X. I ended up with $37.2 billion. So if this trend continues, we can expect about $37 billion. Now remember, predictions are just that, they are predictions. It's quite possible that we might spend significantly more or significantly less. Sometimes our models have limitations. Take a look at this. We're going to predict the amount of spending in the year 1900. We plug 1900 into the equation and we get negative $31.7 billion. Clearly, no one gave us $31 billion in the year 1900 for not developing any space program. And so there is a limitation to this model, and it's quite a ways from where our information was. Notice our information is in the 80s and the 90s, while 1900 is quite a ways off. And so the model isn't so accurate back there. So sometimes you have to use common sense in order to decide if your model really is a useful tool for making predictions in the future or in the past. Simply put, linear regression, again, is the process of writing an equation that represents data. We use it to make predictions, to understand trends, and in order to understand the past. Correlation coefficients tell us how closely our line fits our data. We can have negative correlation or positive correlation depending on the slope of the line. If the data points are very close to the line, we say we have strong correlation. If the data points are quite a ways from the line, we say we have weak correlation. And if they're just scattered everywhere, it's quite possible that we have no correlation. This is everything you need to know to get started on working with linear regression.